Good morning. Today we start a new topic in this course, and here in this particular chapter we will learn about a number of tools and techniques which are used to examine the structure and properties of materials. For example, in the previous chapter we talked about crystal structure. Now, the question comes, how do you know that metals are crystalline? We talked about lattice parameter, but how do we measure this lattice parameter? So, we will come to know some of the experimental techniques which helps us to know number of properties and the structural characteristics of materials. In this chapter, what we are going to look at primarily the tools which are used to examine microstructures of solids. Often it is termed as metallography, but in practice it is actually the microstructural examination of solids, and we have different types of microscope that we will talk about. There is a optical, could be transmission electron microscope, scanning electron microscope. We will look at the main features of each of these. Then we will learn about X-ray diffraction. This is the technique by which you find out lattice parameter of crystals. We will know about number of mechanical properties, and what was mentioned, it is the mechanical properties which is most sensitive to the microstructure of the material, and there are number of mechanical properties which are of great importance, and we will look at some of these. And also to understand how structure develops in solids, it is often necessary to know about thermal analysis. Now, I have sequenced this lecture not exactly in this sequence. I will first talk about thermal analysis and then come back to metallography and X-ray diffraction, and possibly next class we will talk about mechanical properties. Now, first of all, before we start, the question comes, why is it necessary to know about thermal analysis? Because most of the structure that forms in solids, it develops from the liquid when it is cooled, and when crystal forms in the liquid, different types of structures they develop, and in order to know the kinetics and thermodynamics of this transformation, it is necessary to know a little about thermal analysis. And here one of the key tool that we will be using is a thermocouple, which is a temperature sensor. So, let us say what is a thermocouple? It is a temperature sensor, temperature measuring device. It consists of a pair of metallic wire joined at one end, which is shown over here. This is a metal A, let us say this is metal B, and they are joined over here. And if you heat this point, this particular point, if you keep it in a furnace at a temperature T, and we call this as a hot junction, and then we take the output from this end, which is maintained at a room temperature, or we call it cold junction, and we connect it to a millivoltmeter. We will find that depending on the magnitude of this temperature, we get a particular millivolt reading in the meter, and this is a very convenient device for measuring temperature, and the millivolt that we get is a function of the temperature difference. That means temperature of the hot junction minus temperature of the cold junction. And in ideal cases, we will prefer a material, the thermocouple, where this relationship is linear. But in reality, most cases even though it is nearly linear, but may not be perfectly linear, something like this. The millivolt reading as a function of temperature is shown over here. So, this is the characteristic of the thermocouple. And here, in order to measure the temperature, suppose we get a certain millivolt reading, say this is the magnitude which is shown by the meter. Now, since this millivolt is proportional to the temperature difference and this plot may not be perfectly linear, the way of converting it, the temperature is illustrated here. What you do to this millivolt, you add the millivolt corresponding to the cold junction, that is, let us say for the room temperature, this is the millivolt. If you add the two, then this is the total millivolt, and what you do, you read the temperature from here. Now, the question comes, what are the thermocouples, commonly used thermocouples, which are listed here? One is a chromel and alumel. So, one of this, say this is positive, this is negative, and this thermocouple, this is primarily an alloy of chromel is an alloy of nickel and chromium, chromium and nickel. This also is a chromium nickel with a little bit of aluminum, and this is used up to a temperature, I mean quite a wide range. And if you want to go to a higher temperature, platinum 13% rhodium is commonly used. Beyond and between the two, this is more linear corresponding to that. Now, let us look at what is thermal analysis. In a thermal analysis, what we do, say suppose we heat a piece of metal which is kept in a furnace, and we have a thermocouple put into the metal, say kind of touching the metal, here, and this thermocouple is connected to a temperature monitor, and you heat the furnace, I mean you supply power to the furnace, and what we do, we monitor the temperature of this piece as a function of time, and which is shown over here, the temperature as a function of time. Now, as long as it is solid, you will find the temperature goes on increasing, and but when it reaches its melting point, then we will find that temperature remains stationary until the entire amount of solid is converted into liquid, and once it is converted into liquid, again the temperature starts rising. But usually the heating is more difficult to control, because it is involved, as we know, a lot of heat transfer and other features which are involved, the thermal mass of the furnace and lot of other things, and it is often difficult to control the get a good temperature time plot in case of during heating, whereas during cooling you get a much better information, because what you do, you switch off the furnace and let it cool slowly and monitor the temperature, and then which is shown over here. And then this is the melting point. That information that you get from the thermal analysis is the transformation temperatures. So, this is a case where a metal, for a particular metal, pure metal, we find its melting point. But we have much more sensitive equipments for thermal analysis, and these are well instrumented, particularly, so one which is shown here is differential thermal analyzer. So, what you do, you take a piece of that sample, it's a small piece of the sample over here which is put in a container, and you also have a reference material. Now, what you do, you put two thermocouple and you connect them in the opposite way. So, let us say if if this is the negative, you connect this to negative, and then the positives are over here. So, what you are actually measuring is the temperature difference between the sample and the reference. But mind you, this magnitude is very small, you will need an amplifier to magnify it, and what you do, you note down this reading, the difference in temperature, and also you have another thermocouple kept in between, which monitors the temperature of that environment, and both goes to the recorder. And what you plot is this temperature difference between the sample and the reference standard against the temperature of this environment or surrounding, or basically you can say it will be for practically the temperature of the reference material. So, this is the type of plot you are likely to get, and this delta T which is shown over here, and depend the T s minus T r, and what you get is shown here. As you raise the temperature, say suppose some endothermic reaction takes place or transformation takes place, then what will happen? That means some transformation is taking place in the sample, its temperature will not rise, but since the power supply, power is being supplied at a constant rate, the temperature of the reference material will continue to increase. So, then this becomes higher than this. So, this is negative. So, you get an endothermic peak. So, likewise there is a possibility if there is a transformation taking place here which is exothermic, in that case you will get a peak in this direction. So, this compared to that normal thermal analysis, differential thermal analysis gives you little more information. It gives you some qualitative idea about the heat effect and thermal properties. In fact, this area under this peak will be a function of the latent heat of transformation. So, we call it, say, let us say delta H. Maybe it will be a function of the amount of material that you have. It will also be a function of some thermal characteristics of the material, let us say specific heat, thermal conductivity, etc. And it is seen that the sensitivity of this type of measurement increases, the peaks have become sharper, smaller if m is less. Now, there is another variety of variation of thermal analyzer, which is called differential scanning calorimeter. Here, instead of having a common power supply, you will have two independent power supply. Here also you have a reference material and a standard material, that sample, and this is a reference material. Usually reference material is so selected which is very stable, does not undergo any transformation in the temperature range you are operating the system, and this is the sample. And what you do, you connect it in the same way as in the differential thermal analyzer, the DTA, and here also these thermocouples, they are connected in an opposite fashion, and the difference of the temperature between the two is fed to an amplifier, which amplifies it, and it sends that value to a controller. And what the controller does, controller tries to control this temperature difference, it will try to keep it 0. So, that means it has to supply power supply as a differential power supply, different amount of power will be supplied to the reference material and the sample. And in fact, what you are going to measure, the amount of power that you, or heat that you supply to the sample, and the heat that is supplied, power that is supplied to the reference material, and this difference per unit time is plotted in the y axis, and the temperature of the surrounding is monitored by another thermocouple which is fed to the recorder, and you generate a plot of this heat effect, that amount of power which is being supplied, the differential power that is being supplied as a function of the temperature of the surrounding. And here again you will get a similar, the endothermic and exothermic peak, but the sense it will change. This is because an endothermic peak here it will be just opposite of the differential thermal analyzer, and here since it is directly proportional, that heat effect is directly proportional to the power which is differential power which is being supplied, the peak area is proportional to the latent heat of transformation, and it is not a function of thermal characteristics like specific heat and thermal conductivity. So, in short, this definitely is much more powerful than differential thermal analyzer, and it can detect very small amount of enthalpy change or latent heat. And some of these instrumentation, they are also coupled sometime along with that there is a load cell connected. So, you can also monitor the change in weight as well. But let us not bother about it. So, I think what is important, why I spent some time on thermal analysis, because very often to explain how the microstructure evolves in a material, we will be looking at the cooling curves and how the transformation takes place. You can get a lot of informations from DTA and DSC plots. Next, we will come to as has been mentioned. So, once it is solidified, you get a solid mass, and we mentioned number of times that this metallic solid, it is crystalline. And how? So, that means is it the entire mass, is it as one crystal, or is it made up of multiple crystal? How do we know? So, normally for this what we use is we look at the structure of a metal under microscope, and what we do, we take a piece of metal, cut it, we mount it in a plastic. It could be a cold setting plastic, or we can mount it in a bakelite, and then we polish the surface, because metal is not opaque. We have to, if we have to look in a microscope, we have to look at it in reflection mode, and for reflection to occur, the surface should have a mirror finish, it should be shining. So, there are number of steps involved in the preparation of metallic samples for microstructural examination, which is listed here. You cut and mount, then you polish, just mechanically polish, the grind and polish on emery paper. There are series of emery paper with a different grit sizes, and finally, you polish it on a cloth, which is a wet polishing usually, and where you have water and polishing powder mixture, which is put on a rotating disc where you have a cloth mounted on it. So, this process is called lapping, and after that what you do, you etch the specimen. So, normally the polished surface, you put some chemical agent, etching reagent, which will attack certain areas of the metal, and then you put it under microscope. So, which is particularly shown here microscope as a lens, here microscope, this is an objective, and this is the metal piece, and when you etch, it is no longer smooth, Initially it is smooth, when you polish it, it is shining, but when you etch it, number of certain areas dissolve more than the rest, and which is shown here schematically. And when the light falls on the sample, part of it, wherever these faces are inclined, part of this light they get reflected, and so whatever you see through the eyepiece is not the entire light, part of it. So, which is systematic or which is schematically shown here. Say from this part the entire light it goes back, and here I have put it as a dark. So, basically it will show that it is the brightest area, and from this region lot of light gets reflected out. So, less light is coming from that. So, this will have a different contrast. So, what you get is a reflection contrast, and what you find, this metal is made up of it will appear, even if it is a pure metal, it is made up of several crystals. So, like this is one crystal, maybe this is another, this is another. So, they are made up of several crystals, and which we normally call in metallography grain. And extent of etching depends on their orientations. So, what we call it, some oriented grain luster, differently oriented grain gives different luster. And from this microstructural examination, we can get lot of information about the grain size, the shape, etc. in pure metal, whereas in a more commercial alloys there will be multiple phases. Now, this is a typical construction of an optical microscope. As I said that metals are opaque, you have to examine it under reflection mode. You have a light source and you have a lens which makes this light from this parallel. There is a mirror, this is a half silver mirror, part of this light is reflected and it is through an objective, it is focused onto the sample, and the reflected beam also passes through the objective and passes through this mirror, and here you have the eyepiece or you have that image plane where the image is formed. You can put a photographic plate or a camera can be mounted, and this picture or the microstructure of the sample can be recorded. Now, the question comes, what is the resolving power of a microscope? Resolving power, by resolving power we mean what is the ability of the microscope to clearly see two very closely spaced point, which is shown over here. Suppose this point and here, can we resolve them clearly? We will see them as distinct constituents or distinct points, and this distance, if this distance is lambda, it is a function of the wavelength that we use to examine the microstructure. An optical microscope, what we use is the visible radiation, and visible radiation has wavelength, as you know, around say 4000 to 6000 angstrom, and this resolving power is equal to the wavelength over twice numerical aperture. This numerical aperture means amount of the light which comes in, which it is a measure of. So, basically this numerical aperture is a function of the refractive index of the medium here, this medium. So, in most cases it is air, let us say, and it is also function of this angle, this particular angle. Now, the maximum angle, this angle, the maximum angle, it can be 90 degree. In that case, this objective almost virtually will be touching the eyepiece. So, this is the limit. So, if we say that it is possible to reach that, so that in that case we can say that this is one. So, basically this resolving power has a direct relationship with the wavelength that you use. So, resolving power approximately we can say in this refractive index of air is 1, this is 1. So, we can say it is of the order of, it is an approximation of the order of lambda over 2. So, if we use the smallest wavelength, the violet region, we can expect that 2000 angstrom to be the resolving power of the microscope. Now, in the optical microscope, although we get an idea how the different grains in an optical microscope, how the different grains are arranged in a solid, that impression we get from optical microscope, but optical microscope will not give us the crystal structure. What is the crystal structure of that particular grain? Because metals, they are deformable, they can take any shapes, they can be made to take any shape, unlike rock where there are different crystal faces are quite prominent. This is not so in metal, and in fact, that the metals are crystalline were first experimentally proved only when X-ray diffraction technique was discovered. And X-ray diffraction, what we use is an X-ray beam, and X-ray it is an electromagnetic wave. It has a very small wavelength. As we said that resolving power is a function of wavelength in case of an optical microscope. In fact, if this wavelength becomes very small, it is possible to resolve even the crystal structures of solids. And X-ray, it has a very high penetrating power also. It can pass through thin pieces of metals. In case of steel, it will be thin, but in case of aluminum, even quite thick samples of aluminum, the X-ray will be able to penetrate through. And how do you get X-ray? Basically, it is a vacuum, it is a tube which is in a vacuum tube, a tube in vacuum, and you have a filament which is heated, and if you heat the filament, you get electrons emitting from the filament, and this electron is accelerated to a very high voltage of the order of several kilovolts, say 30 or 40 kilovolts. So, what you will have? You will have a stream of electron moving in this sealed tube, and then it strikes a target. These targets are made up of metals and which are water cooled, and from this metallic targets you get X-rays emitted, because what happens, this beam of electron has high energy, and when this electron strikes this, it loses that energy, and part of this energy is emitted as X-ray. And intensity of X-ray, that its distribution is shown over here. This is intensity as a function of wavelength. You get this type of plot. There are certain peaks also which are noticed. These are characteristics wavelengths of corresponding to this metal target. So, these are called K alpha and K beta radiation, and this you must have read in physics. These are the characteristic emissions from a metal when they are excited, because we know that electrons and metals, they are moving in different orbits which like K, L, M, N. Now, if this electron which is striking the metal target removes an electron from the K cell, then it becomes it goes to an excited state, it is unstable, then an electron from higher orbit, say L, drops down to K, and in that case you will have K alpha radiation emitted, and if an electron drops from M to K, you will get K beta radiation. Now, this wavelengths of this characteristic wavelength, this is a function of atomic number, and very often in X-ray diffraction we use some specific characteristic radiation like copper radiation, copper K alpha has a wavelength of 1.54 angstrom. Similarly, we also use chromium K alpha or molybdenum K alpha radiation to record diffraction pattern, and often in other cases we also use the white radiation to record diffraction pattern from single crystals. And in case of white radiation, we will prefer usually tungsten target. For monochromatic radiation, we usually prefer the characteristic radiation from certain specific metals like copper, chromium, molybdenum, etc. Now, X-rays, they are electromagnetic radiations, they have very small wavelength, and now imagine if that X-ray is incident on a crystal which is represented over here as a regular array of atoms represented by these points, and these are two crystallographic plane. Now, if this beam is incident at an angle theta, this is the incident angle, the angle of reflection is also equal to theta, this is the reflected beam. Another beam which penetrates, because it can go into the metal, which will penetrate the metal and get reflected from the next plane, and this is the reflected beam, and this two path, they cover different distances. This covers longer distance. As I said, we are familiar with the wave characteristic of X-ray. These are electromagnetic wave, and when these waves interfere, waves having covered different paths, they interfere, you get an interference pattern or diffraction pattern. And it is possible to calculate the path difference here in terms of the d spacing. This is the interplanar spacing d. Now, path difference is made up of C B, this path, you drop a normal from here onto this and a normal from here onto this. So, total path difference is C B plus B D, and both of these are equal. It is possible to show that both of these are equal. See this angle, say this angle also is theta. So, this is 90 minus theta, this is perpendicular. So, this is theta. So, B D is d sin theta. Similarly, C B also d sin theta. So, total path difference is d sin theta, and when this d sin theta is an integral multiple of wavelength lambda, then the waves are in phase, you will get intensity maximum. When they are out of phase, there will be destructive interference. So, what you will get in certain directions, certain values of theta, you will get intense peak, whereas in other values of theta, the intensity of the beam will be minimum, will be very less. Now, a little you can rewrite this expression in a different way. Say if you say that n lambda over 2 d is equal to sin theta, we know that sin theta is always less than 1, much less than 1. So, therefore, you can see in order to get diffraction pattern, the wavelength of X-ray has to be substantially less than the lattice parameter of the metal. So, like copper, I said the lattice that K alpha radiation, the wavelength is 1.54. Now, if you want to record a diffraction pattern of copper with this copper K alpha radiation, it is possible, because lattice parameter of copper is around 3.6 if I remember correctly. So, it is less than, much less than, so around half of the lattice parameter of copper. So, it is possible to record diffraction pattern of copper using copper K alpha radiation. Now, how do you record a diffractor and this diffraction pattern? This is schematically shown over here. Say we have a sample which is kept over here. This is the incident beam, this is the transmitted beam, and the beam is diffracted here. And if you go back to the previous one, see here this is the angle theta between the diffracted beam and the reflecting plane. But if you extend this, this is the transmitted beam, if you extend this, this is the transmitted beam, then the angle, this is theta, this also, this is theta, you extend it, this angle is theta. The angle between the transmitted beam and the diffracted beam is twice theta. So, which is shown over here, this is the diffracted beam, and what you have on this, around this circle, we move a counter which can detect the intensity of X-ray. So, in fact, a diffractometer is a device where you can place the sample on a stage called goniometer, and this can be rotated also, this can be rotated about different axes. And what you can do, there is a counter which moves along this circle and records the intensity as a function of that angle of diffraction, that is 2 theta, and which is shown over here, the intensity as a function of 2 theta, and certain places you will find that suddenly you get a very intense peak, and this intensity of these peaks is a function of several factors. It is apart from the indices of the plane, it depends on the deflecting plane, it depends on the arrangement of grains in the structure in this particular material. So, in short, I have put here the intensity is a function of structure, microstructure and texture, how the different grains are oriented apart from the crystal planes and the Bragg angle, that is 2 theta. So, in fact, we can look at it diffraction. After this, let us look at transmission electron microscope. Now, we looked at optical microscope, and while discussing optical microscope, it was mentioned that resolving power of the optical microscope is of the order of wavelength of let us say wavelength of visible radiation. So, the maximum resolving power that you can get is of the order of 2000 angstrom, but metals are crystalline, its lattice parameter is much smaller, and therefore, and to record their crystal structure, we make use of X-ray diffraction techniques. Now, are there any other better method or where we can resolve the lattice structure much more clearly? Or so, one possibility is to use much smaller wavelength, and electrons, as we know that if the electrons move at a high velocity, it also has a wave character. Wavelength of X-ray is of the order of few angstrom, like for copper K alpha radiation it is 1.54. Whereas, electrons, if they can be accelerated, let us say for 100 kilovolt or more, that wavelength, its wavelength will be even smaller, and it also can penetrate thin foils of metals. In that case, unlike optical microscope, if we look at this transmitted beam passing through a thin foil of metal and we can magnify with a lens, it is possible to resolve much finer structures of metals. And this principle of operation of this transmission electron microscope is given in this slide here. Unlike optical microscope, which operates in reflection mode, this operates in a transmission mode. the sample, which is a thin foil, is placed over here. You have a filament, tungsten filament. If it is heated, it emits electrons, and this electron can be accelerated by applying a large voltage between the anode and this cathode, that is the filament, a high voltage of the order of 100 or 200 kilovolts, and this and the ray of electron moving at a very high speed, will pass through. They can be condensed using lens. Now, unlike in optical microscope, we use glass lens. So, here you cannot use glass lens. Lenses are made up of magnetic coils, or magnetic operates on the principles of electric and magnetic fields. By controlling these, it is possible to make the beam parallel or make and focus it onto the specimen, and after it comes out, you can enlarge it in an objective in the same way as in an optical microscope and form an image over here. You can also, this is the back image plane, and you can also magnify it further like a eyepiece, and this magnified image falls on a fluorescent screen, and you can see the optically, visually you can see the microstructure of a piece of metal at a much higher magnification. You can also put a camera here and record the microstructure, but the sample has to be very thin, and which is and it takes a lot of skill to prepare the sample. And regarding the wavelength, it has a direct relationship. The wavelength corresponding to the of that electron beam can be calculated in terms of using this expression. This is root over around 150 over voltage, and this gives you wavelength in angstrom. And if you calculate this, about even if you use 100 kilovolt, you get a wavelength of 0.039, which is much smaller than the wavelength of X-ray. So, its resolving power is much more, and it can also penetrate thin foil. So, therefore, its resolving power of modern microscopes are very close to this atomic plane resolutions. So, it can go to of the order of angstrom, 1 and 2 angstroms. It is often possible to resolve crystal planes in transmission electron microscopy. But the main problem is sample preparation. These techniques use, some of these are listed here. You can take a replica. On what you can do on the piece of metal, you can deposit a layer of carbon, and you can then float that replica by dipping it on water, and that replica can be fished onto a copper grid, and that grid can be kept or placed in the microscope here as a sample, and that carbon foil gives an image of the top surface of the metal, and sometime by using some special etching technique, it is possible to extract some of the particles from the metal surface, and you can also look at how these particles are distributed, can also be seen. But you can get lot of information. You can make metallic thin foils, and this is made by, there are two common techniques are electropolishing and iron milling, and it needs a lot of skill and practice to prepare a good thin foil for examination under transmission electron microscope. Now, how do you get that like an optical microscope, because certain beams are reflected out. So, you get some image contrast in case of an optical microscope. Now, how do you get an similar type of contrast in transmission electron microscope is illustrated over here. So, this is the electron beam passing through the metal foil. The metals are crystalline. The certain parts of the metals, they may be favorably oriented to diffract this beam. So, these are the diffracted beams. The dotted line, this diffracted beam, and you have a lens over here, that objective lens here. This objective lens will focus these beam, this transmitted beam onto this point, this diffracted beam onto this point. Now, if you place an aperture over here, then you can block the diffracted beam. Then you get a contrast, this area will appear bright, whereas the areas from where most of these beams are getting diffracted will appear dark. So, the grains and subgrain or subgrains whose orientation satisfies Bragg condition will diffract and they will appear dark. Now, here one may question, I said that sample should be a very thin foil, thickness should be small enough, so that the beam does not get absorbed, it just passes through. Now, this order of foil thickness is a function of several factors like atomic number of the metal, the voltage that you apply, the kilovolts, 100 kilovolt, 200 kilovolt, possibly you will be able to examine relatively thicker specimen. Similarly, the density of the foil, that the metal of which the foil is made up of is also an important factor. And if you are looking the microstructure of aluminum, say something like 0.05 to 0.5 micron, you may be able to examine under, has to be much thinner than this. And sample preparation, of course, as I mentioned, needs lot of skill and practice. Now, besides transmission electron microscope, we also use scanning electron microscope. Now, the principles of imaging in a scanning electron microscope is entirely different from a conventional microscope. Now, as far as construction is concerned, is more or less certain features are very similar to the transmission electron microscope. You will have a filament, you will have an anode, the electrons emitted from the filament is accelerated to a high voltage. You will have lens to focus and or condense to focus it on the sample. Now, here in addition you have a magnetic coil here, which can move this electron beam. Suppose if this electron beam falls straight here at one point. Now, you apply some voltage here, in that case you can move it from here to here. Similarly, you apply another voltage, you will shift it from here to here. So, what is done? There is a scan generator which generates a scanning voltage, and what it does, it scans, it shifts, it keeps shifting this beam from one point to the other in the form of a raster, like something similar to a TV screen. And what you collect from here is when this beam strikes, so some of the electrons are reflected and some penetrate a little and some secondary electrons are emitted, and you get maximum information if you can collect this secondary electron in this collector over here, scintillation counter, and this signal is amplified, and what is this amplified signal is fed to the oscilloscope and it modulates the intensity of that raster, that is the TV screen, that raster that is generated, and that is how you generate the image of this surface over here. And usually the sample is slightly tilted, and so basically, so here you do not have that type of that imaging, is entirely depends on how well you can converge the beam to a particular point. If that point is very small, it will have high resolving power, and how well you can scan and at what interval you can record that intensity and modulate to generate the image of the surface. Now, main advantage of this type of microscope is its resolving power definitely may not be as high as that of transmission electron microscope, but it has one important property, that is depth of focus. So, like in optical microscope, if you want to see the microstructure at a very high magnification, you have to have excellent surface finish. It should be mirror finished. You should be able to bring that objective very close to the sample, which whereas in this particular case it is not that critical. The sample preparation, a sample surface can be much rough, even you can record the fractured surface as well. So, with this what we have looked at today, we looked at main features of 3 different types of microscope that we use, that is optical microscope, scanning electron microscope. We also looked at X-ray diffraction techniques. We stated the condition under which diffraction takes place, that is Bragg's law. It may be worthwhile to look at that Bragg law a little more carefully. What has been mentioned here, that is 2 d sin theta equal to n lambda, which can be written like this, and therefore, it is possible to find out what should be the wavelength, so that you can record a diffraction pattern. So, this is the lattice parameter, this is the Miller indices of the reflecting plane, and this is an integer, it calls the order of the diffraction patterns. This n can have value 1, 2, 3, etc. And very often we say in X-ray diffraction, instead of saying the reflection comes from plane HKL, we say the reflection comes from NH, NK, NL. Now, to record a diffraction pattern, one point is very critical. This is the incident beam, this is the transmitted beam, this is the diffracted beam, and as has been mentioned, it subtends an angle 2 theta. Now, this is a reflecting plane. Now, this diffraction occurs only if this condition is satisfied. Now, suppose your beam is monochromatic, lambda, this is fixed. So, to get a diffraction pattern at this particular place, you have to have a particular crystal which will satisfy this relationships, and this can be done in 2 ways. If you have multiple crystals, the one of these planes, some of particular plane will satisfy of a particular crystal will satisfy this, which can be visualized like this. You have several planes, say like this, and all planes which are subtending an angle theta will give you a diffracted beam. And if you have a very large number of crystals, you can visualize, that means you have a diffracted beam coming out in the form of a cone. And this type of cases where your sample is made up of large number of crystals, we call this diffraction technique as a powder diffraction technique. And in physical metallurgy, mostly we will talking about, or we will be, this is the technique which is most commonly used in physical metallurgy. It is also possible to record diffraction pattern of single crystal, but in that case you need to, since this becomes fixed, to satisfy this you must vary, this becomes variable, and in that case that type of diffraction pattern or technique is called Laue technique. And nature of the diffraction pattern will be totally different. In case of a powder diffraction pattern, you get the diffracted beam comes in the form of a cone, which is something like this. So, if you put, say, suppose it is possible to put a film surrounding it, you will get in the film, this is a transmitted beam, you will get diffracted lines like this. So, with this we come to the end of today's lecture. We looked at thermal analysis. Thermal analysis, it is important because it helps you to determine transformation temperatures. It is also possible to know a little bit of information about the thermodynamics of transformations. To some extent, there are other techniques also to follow the transformation, like measuring other physical properties like coefficient of linear expansion, resistivity or magnetic property if the material is magnetic. But nevertheless, thermal analysis has been most common extensively used to look at the transformation processes in materials. We also looked at the principles of or how we prepare samples for microscopic examination, optical microscope, the simple polishing and etching. You can look at the microstructure in a reflection board. If you go to the transmission electron microscope, you have to prepare thin foil. On the other hand, we looked at scanning electron microscope, where sample preparation is not that critical. You can even look at the structure of a fractured or very rough surface. With this, we finish today's lecture, and in the next lecture we will talk about mechanical properties. We will know certain types of mechanical properties which are important and how they are measured. Thank you.